Okay, welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 1.1, day 2, and section 1.1 in your book is entitled Real Numbers. And the concepts that we're going to be talking about today are the bottom 3 objectives that are listed here. We're going to review the real number line, and then we're going to talk about something that is a little newer, set notation and unions and intersections. And then we're going to talk about absolute value and distance. And the way that they approach distance is a little bit new for you guys too. So the real number line, I'm sure you're very familiar with it. This is an example that I believe is also in your book. Any number that you can think of, any real number, can be represented on the number line. You can plot the point wherever it is located. And remember that 0 is going to be in the middle of your number line. And then as you move to the right, you're going to have more positive values. And as you move to the left, you're going to have your negative values. You can have whole numbers, you can have fractions, decimals, square roots, rational, irrational numbers, anything can get plotted on the number line. And it helps us to put numbers in order, and it also helps us to make inequalities, which again is a concept that you know. But here are just some examples of how we can make inequalities with the number line. When you're comparing numbers, you can plot them on the number line, and then you can see that 7 is less than 7.4, which is less than 7.5. So it's a visual representation of those inequalities. Now this set and interval notation, this is new stuff. I know you've talked about sets, and you might have done the set notation, but you haven't seen elements yet. You haven't heard it talked about in this way. So a set is a collection of objects, or in our case, numbers. And a set has elements. Sorry about that. The set has certain elements. And to show that an element is part of a set, you're going to use this new notation over here. This little, looks like a little E. So if A is an element of S, you're going to have A and then the little E symbol that means element, and then capital S is for the set. So that means A is a number in whatever set S is. And then we also have a negation for that. You could say B is not an element of S. So you'd have that little E symbol and then a slash through it. So if Z represents all of the integers, so Z is the big set of all integers, then -3 is an element of Z. -3 is an integer, but pi is not. Pi is not an element of the integer set, because 3.14 is not an integer. And some sets can be described by listing their elements within the curly braces or the brackets. So that's what we see down below here. We have the first 7, or I'm sorry, not the first 7, but the first 6 integers. All the positive integers less than 7. So you'd have 1, 2, 3, 4, 5, 6. So A is the set of all of the positive integers that are less than 7. So you can just list them inside the curly brackets like that. And we've also seen set builder notation, and you might have seen this a little bit last year in Algebra 2, depending on who you had. Sometimes it's just called set notation, sometimes that builder is left off, and it's just called set notation. But you say what the set is, so here we have set A, and then equals is, and then you're going to have your curly bracket, and then you say what the element is. So here you have x, and then you have this line, this vertical line, and that's read to be the words such that. So x is an element such that x is an integer and x is less, or 0 is less than x is less than 7. So everything after that line such that tells you what x is. So we're going to practice using this set notation more this year. You're going to get very comfortable writing it. And along with this set notation, we also have 2 new concepts. We have unions and intersections. And a union has a symbol that looks kind of like a U. It's right here. So we have set S and set T, and we want the union of them. So that means you want all the elements that are in S or T. So you want to include every element that is in both sets. That's what a union is. An intersection has a different symbol. It looks like a little upside down U. So for a union, it kind of looks like an actual U. And for an intersection, it's got a little N. It kind of looks like a sloppy N, sloppy lowercase n, or an upside down U. And this means that you want everything that's in both, or I'm sorry, only the elements that are in both. So it has to be in S and T. So I also think that and has a little N in it, and this upside down U for the intersection kind of looks like a sloppy lowercase n. So that's how I remember which is which. If you want to come up with your own way to remember, that's great too. So S intersection T is the common part of S and T. It's the stuff that they both have. It's where they overlap. Okay? And we have an example coming up that's going to show this a little bit more. But before we move on to that, we also have the empty set. And you've used this symbol a lot. That's the circle with a slash through it. That means that there is nothing in the set. It's a set containing no elements. You sometimes use it for no solution. So for example 4 here, now again, this example is in your book, so if you'd like to follow along there, you can. But here we have the set S, and it has the elements 1, 2, 3, 4, 5 in it. And then we have the set T, which has the elements 4, 5, 6, and 7. Now notice that some of those overlap, some of them are the same. And then we also have set V, which is 6, 7, and 8. So again, that has some overlapping with set T. And we want to find each of these sets. So our first one here is S union T. So we want to find what is in the union of S and T. And remember, that's what S and T have all together. We want to include everything in S and everything in T. Now there is some overlapping. S and T both have a 4 and a 5, so I'm not going to count them twice. I'm just going to list them once. So we'll have 1, 2, 3, 4, 5, and then 6 and 7. So that is everything that is in set S and set T. That's what a union is. And they also want us to find S intersection T. So that's the stuff that's in S and in T. It's the stuff that's in both of them. So again, we noticed that when we were doing our previous example. So the stuff that's in both of them, the stuff that overlaps, is just the 4 and the 5. That was the stuff that I said I wasn't going to list twice. And then our last one that we're going to practice here is finding S intersection V. So this is the stuff that is in S and in V. And S has 1, 2, 3, 4, 5. V has 6, 7, 8. They have nothing in common, so that's our empty set. Okay, moving on to our next little bit about sets and intervals is that anytime we're talking about a set of numbers, we can look at it for a specific interval. So sometimes you only want to look at a certain number from, or a certain behavior on a graph from the number -5 to the number +5. So that would be your interval from -5 to 5. And we have open intervals and we have closed intervals. Open intervals you've seen when you graph on a number line and you put an open circle, that's an open interval. So that looked like this when you've done it before. You had your open circles and you would shade between them. That's an open interval. And we're going to represent that now without having to draw the picture. We're going to use those little parentheses that they have listed there, the A and the B. So now instead of having open circles, we're going to have parentheses to represent that openness. And you've done closed intervals as well. When you graph them on a number line, you make solid circles and then you shade between them. And again, we're going to represent this without having to use a number line. We're going to represent it with these closed brackets that they have listed there. So the parentheses now are going to represent the openness, and the brackets are going to represent the closedness. And A is going to be your first value where the interval starts, and then B is going to be your value where the interval ends. And we're going to combine this with our set builder notation that they have down here at the bottom. So our open set from A to B means anything that's between A and B, but it doesn't necessarily include A and B because it's got those open circles. And the closed set from A to B means everything from A to B, including A and B. So A and B could be actual values in your solution. And this just kind of restates what I drew on the other page. The parentheses now are going to represent those open circles, and the closed brackets are going to represent those closed circles. And this diagram is in your book. This shows you pretty much every combination that you could have of open sets and closed sets and some combination of them. You could have a completely open set with parentheses, or you could have a completely closed set with brackets. You could have one part be closed and the other part be open, or vice versa. And anytime you go to infinity, infinity always has openness around it. So you could have something that starts as an open bracket and then goes to positive infinity. You could have something that starts with a closed bracket and goes to positive infinity. Even negative infinity also has an open bracket because we can't really quantify infinity. So it just goes forever. So we want to keep it as an open concept. And then if you're going from positive infinity to negative infinity, that's the set of all real numbers. That's going to be open on both ends of your notation. So make reference to that chart if you need to as you're doing your homework. Okay, so for example 6 here, we're going to graph each of these sets. Now this is what's new. Here you've got your set notation and your interval and your intersection. I'm sorry, your union and your intersection notation. So it's taking two somewhat new concepts and putting them together in one problem. But we can draw this graphically if we'd like to. Okay, in part A, these parentheses from 1 to 3, that's going to be our open interval from 1 to 3. So let me just draw a little number line here. 2, 3, 4, 5, 6, 7. So if I'm on the open interval from 1 to 3, that means I'm starting at 1 and I'm going to 3. I'm going to have open circles. I'm going to go between them. And then I'm going to draw another line, another number line down below it. I'm going to try and draw the exact same one. Oops, that's 1. And then 2, 3, 4. Oh, goodness. Put my number line back in there. There we go. 5, 6, and 7. Okay, now for my closed set here, I'm starting at 2, and I'm going all the way until 7, and I'm going to have closed circles, and I'm going between them. So now, remember, for this symbol here in the middle, this little upside down U kind of looks like an and. That means it's an and concept. You want to find the stuff that's in 1 to 3 and 2 to 7. So you want the stuff that's in both of them. So it's kind of like wanting the stuff where they overlap for that intersection. So you could kind of even think of it like drawing little dashed lines that come down here from the 2 and then to the 3. That's the part where they overlap. Okay, and that's the stuff that they have in common. Now if I'm starting at 2, that's fine, but remember 2 was closed on one interval, so we have to have 2 closed in our solution. And then 3 is going to be open for both of them. Okay, so that is our solution set. And for part B, you could draw the same diagrams if you would like. However, this one isn't an intersection. This, they're asking for the union because we've got that little U symbol. So we want to find everything that is between 1 and 7, basically. If we're doing a union, that means we want everything from each set. So I don't really need to draw the pictures here because I know I'm starting at 1 and I'm going all the way to 7. So that is my set notation. Okay, last concept then is absolute value and distance. You're familiar with absolute value. Absolute value has these little bars around it, and it shows how far a number is from 0 on the number line. So it's a distance, and it always has to be positive. The distance has to be positive. You don't lay down a ruler and say, oh yes, that's -3 feet long. We have negative distances, but the negative stands for going below ground or below 0. And here they have the definition of absolute value, but I think you're already fairly familiar with absolute value and figuring out how far a number away is from 0 and remembering that it's already positive, or it's always positive. So just a quick review for part A here. The absolute value of 3 is going to be 3 because it's 3 units away from 0. Absolute value of -3 is also 3. It's also 3 units away from 0. Absolute value of 0 is 0. 0 is 0 units away from 0. Now part D, this one's a little bit tricky. And the best way to go about this one is to think of what pi actually is. So pi, here we have 3 minus, pi stands for 3.14. And I know we have way more decimals than that, but I'm just going to use 3.14 for right now, just to illustrate this. Okay, so there's my absolute value bars. Now if I take 3 minus 3.14, I get a negative 0.14. And again, I know there'd be way more decimals, but I'm just illustrating. And the absolute value of that is 0.14. And to get 0.14, I would take pi minus 3. So the absolute value of 3 minus pi is really pi minus 3. That's how your book is going to interpret that. And this table here is also in your book, and it just is a refresher of some properties of absolute values. The first one says that when you take the absolute value of a number, it has to be greater than or equal to 0. The second property says that the absolute value of a positive number and the opposite of that positive number, it's the same thing. Here you can multiply absolute values inside or outside the bars. And then here you can divide as well. If you're dividing inside the absolute bars, you can break it apart and do absolute value of the numerator, absolute value of the denominator. And again, those concepts you should already know. And then they're going to apply those rules to this concept here about the distance between points on the real number line. So it says if a and b are real numbers, then the distance between the points a and b on the number line is basically b minus a, and then the absolute value of that difference. So basically that says that the distance from a to b is the same as the distance from b to a. So the distance from -2 to 1 is the same as the distance from 1 to -2. So that's our last example here, finding the distance between the numbers -8 and 2. So if we're going to use that equation that was on the previous page that was just listed, we would take our -8 minus 2, take the absolute value of that. You have to simplify inside the absolute value bars first before you take the absolute value. So our absolute value, or the distance between those two numbers, is 10. And you can verify that graphically. You probably don't have to use the formula to even get that answer. You should know that -8 is down here, there's 0, there's 2, and the distance between them to go from -8 to 2, you've gone 8 spaces to get up to 0, you've gone 2 more to get up to the 2, 8 plus 2 is 10. Okay, so that whole distance is going to be 10. get used to using that formula because that formula for distance and absolute value comes back later on as we go through the curriculum. So there's your practice problems for tonight. Again, remember you're just doing 39 to 49 odd. That little O stands for odd. Remember that. And 55 to 75 odd. Okay. If there's ever a little lowercase e, that'll be the evens. So good luck, do well. If you have questions, come on in and see me.